This book is, I think it's fairly easy to read, but it's hard to understand. That's been my experience. Uh, Partly because the whole biogeochemical arrangement of life on Earth is mystifying. So he's talking about, he has his title, How Our Planet Came to Life. I may have said this previously. Nobody explains where life came from. That is utterly unexplained. I show a slide or two of simple organisms, there is no such thing as a simple living organism. So that question won't get answered, how our planet came to life. Once it came to life, it has diversified into millions of species and filled every niche on the planet in the atmosphere and underground. So I'm going to read this little introduction from Ferris. He first argues life does not merely exist on Earth, but rather life is Earth. There's more to this. There's more to this, but I'm going to parenthesize here and say some of this is hard to grasp and maybe a little unnerving. I mean, it has perhaps something that could be considered certainly spiritual overtones, possibly religious overtones. He certainly never touches religion in any way, and we're not talking religion here. But there is a complexity and mystery to life that is incomprehensible. So, going back to his quote, life on Earth acts as an active force that fundamentally transformed the planet's atmosphere, oceans, and geology over billions of years. The book posits that Earth is a singular, self regulating, interconnected living system, challenging the view that Earth is just a rock. It's a worthy argument. It might be discomforting, might not be true, but it's a worthy argument, and he spends the journey in the book making the case for that. And I showed this slide, I think, last week. I am quite fond of this slide. It's an oxygen atom, so I have here, I looked up, you can Google everything. I Googled how big is an oxygen atom? An oxygen atom is 1 million times smaller than the diameter of a human hair. And yet these elements, oxygen and the other, I think, total of 94 naturally occurring elements, but there are five or so that are the most important for life on Earth, one of which is oxygen. They're indescribably minute, indescribably abundant, and they all have a highly refined physical structure. So here we have the physical structure of oxygen. It shows the electrons. Oxygen has 8 electrons. The first two, if an element has 2 electrons, it always goes in the first orbital. So you see the inner orbital there has two little dots representing the two oxygen electrons. Any more than that go into the second orbital until it has, I think, 8. Till it has 8. The second orbital holds 8, but this oxygen only has so many electrons. It has 8 electrons, so there's only 6 left over for the second orbital. So in a sense, in an anthropomorphic sense, it wants to fill that orbital. It wants 2 more electrons. Oxygen is one of the most highly reactive elements because of this phenomenon that the second electron orbital is not full and it wants to fill it, speaking anthropomorphically, admittedly. But it's one of the most reactive elements for that reason, and it drives a lot of the processes of life. So I love this quote at the bottom by Christian de Duve. Life may be an obligatory manifestation of matter, because matter, which are the elements, wants to complexify. It's inevitable when they meet other elements. I mean, oxygen will join with another oxygen atom. In the atmosphere, it's O2, two atoms, but they share electrons and both of their orbitals are full. So this intense order of our planet and the universe is built into the structure of the universe. I find that stunning. Some of you have seen this cartoon before, one of my very favorites. Excuse me, I think I put in human. Oh, I didn't. I tried to put in human there to replace man. I know that could be offensive to non-men. It's just the way it goes. I did put human in, but I don't know where it went. Just not showing up. Anyhow, humans, evolutionarily, all life started as a single cell. I think the next picture is of a single cell, and it's indescribably complex. So it's not that it was so simple. All you needed was a nucleus and a nuclear membrane or a cellular membrane, and life appeared. No, where did these things come from? We don't know. But life has complexified since then. Humans have, I'm sorry, I always forget, trillions of cells, all working together to make our lives possible. But we start out as a single cell, literally. We start out as a single cell, a fertilized egg, and it has all the information in it to make a human being. It's a miracle. It's just a miracle. So I Googled, I constantly, for this program, I'm constantly Googling. Google knows everything. So I says, what are the smallest organisms? And came up with this mycoplasma genitalium, which, yes, indeed, is a parasite in the human genital system. But if you're a parasite, it means you don't need very much DNA and you don't need any energy because you suck it all from other organisms. But it is a living organism. It's a bacteria. It's a living organism. And let's see what I have here. It's 0.4 micrometers. We don't know what a micrometer is. I think a micrometer is a millionth of a meter. But for one bit of size comparison, this living cell, this one of the smallest living cells, is 140th the diameter of a human hair. And yet it has a life of its own. It functions within its cellular membrane. So it's a bit of a jump to the Amazon basin, but we go there. Most of the chapters in this session were spent in the Amazon basin. There's a lot of life in the Amazon basin. It's the largest river basin in the world, 2.7 million square miles, covers almost half of the South American continent. And it drains more water to the ocean than the next 9 largest rivers in the world combined. So it's a notable phenomenon. And I'm pulling up here this Amazon Tall Tower, which was set up in the Amazon to study the biological dynamics of the Amazon basin in whatever way they could do that. But surprisingly, a lot of what this tower does is test the microparticles in the atmosphere released by the forest. So who would think of that? It would never enter my mind to test that, but that's what that tower is for. So, what aspects of this image are a product of life? Well, obviously the trees are alive. Yes, we tend to think the environment shapes life, but life also shapes the environment. So, what aspects of the environment here have been shaped by life? Well, obviously the forested ground. Those are living organisms. The earth itself, the rocky matter that was originally the ground is now organic matter known as soil because it's been altered by life. Those trees are pumping enormous amounts of water into the atmosphere, creating those clouds. So the clouds are also a product of life. And the blue sky is created by light reflecting off of the O2 molecules, the oxygen, 21% oxygen in the atmosphere, all of which was pumped there by life. So everything you see in this picture is a product of life. So I like this line. I don't forget if it's out of the book. Do forests grow where it rains? Or does it rain where the forests grow? And the intimation here is that it rains where the forests are. And the fact of the matter is that forests, by the dynamics of their structure, pump enormous amounts of water into the atmosphere on a daily basis. Let's see if I can find the numbers here. So in the book, the numbers are 20 billion tons of water are pumped into the atmosphere every day by the Amazon rainforest. That's 5 trillion gallons. It's almost as much water as runs down the Amazon River every day. is pumped into the sky. So you do have, in fact, an atmospheric river in the sky created by life. It's a biotic pump, a biological pump. Here's a little more biological pump. So the author, Ferris, spends some time talking about the fact that rain is a little more complicated than we tend to think of it. Water vapor can condense into liquid water and fall out of the sky as raindrops, but it tends to the condensing water tends to form around solid particles that are pumped into the atmosphere by life. So he calls these condensation nuclei, and they would be, he has listed pollen grains, fungal spores, bits of organic matter, which can be microscopic and blown up into the sky. So you have far more of these in a rainforest than you have in a desert, infinitely more. So what you end up with is the forest beckoning rain by pumping these organic particles into the atmosphere that become condensation nuclei. The forest makes it rain. So as we all know, there are issues with the Amazon rainforest, and that issue is it's being cut down. I have to look here. I think 20%. Should have put it on there, but something like 20% of the rainforest is no longer lush rainforest. It might be replaced by organic organisms, but a lot of times it's grass. A lot of times it's pasture, a very different plant than a tropical tree. And so it's thought that we talked a little bit about this biotic pump. I used the term there. The trees pump nuclei, organic matter into the atmosphere, which create condensation nuclei that then cause water vapor to condense around the nuclei and fall as rain. So the trees are beckoning rain. The biotic pump, the fear here is that if the trees are cut down, that biotic pump will cease to work. And I have not mentioned yet that one of the dynamics of that pump is to suck atmospheric moisture in from the Atlantic Ocean, where there's no mountain range. There's a mountain range over there on the Pacific side, but there's no mountain range on the eastern side. And it's so the pump actually will suck additional water in from the atmosphere. If the trees are cut down, that'll all come to a stop. This dynamic interaction of life in the atmosphere will cease. So something like 20% of the Amazon basin is no longer rainforest, and they're still certainly cutting at it. Many people are trying to protect it. So enter fire. We haven't talked about fire, but where you have organic matter, you tend to have, at some point, fires. You have fires in the Amazon rainforest. I mean, natural fires in the Amazon rainforest. There are natural dry cycles, and nothing like in our American West. But you have wherever there's organic matter, organic matter is basically a hydrocarbon, carbon and hydrogen bound together, and it gives off energy when that hydrocarbon bond is broken. So oxygen will break that hydrocarbon bond. That's when we eat food. That's where we get our energy. That's why we breathe. It goes into our digestive system and meets the organic matter that we eat as food, and it breaks the hydrocarbon bonds, and it's transferred somewhat miraculously into energy to give us our lives. Well, that energy is always available in hydrocarbon bonds, which starts out as photosynthetic organic matter, which burns because it has energy in it. It burns. And the main point of this map is that everything with organic matter becomes a potential fire regime, and everything over time in the contiguous United States, but obviously any place there's organic matter will burn. So fires are a natural part of any ecosystem with organic matter in it. So this shows burns over time period. See if I have any circles here. No. Burns in California. California is actually a semi-arid environment, and it does burn regularly. And so that large blue column shows prehistoric annual acreage burned by fires, 4 million acres burned by fires. Well, it's hard for humans to coexist with fire. It damages some of our human structures. So we have been putting it out for the last at least 150 years. And that has built up to this buildup of fuel, of organic matter, everywhere. And so now we're faced with the problem of naturally occurring fires taking off and burning that accumulated organic matter. So I actually took these pictures from my porch 10 years ago, 11 years ago. This is a Carlton Complex fire. This is not too far from where it started. In fact, you can see that fire must have just started on the right, under that ponderosa pine. So while we live in a fire-evolved ecosystem and fire is natural in our ecosystem, because we have suppressed fires, there's more organic matter on the ground, thicker forests, and the fires are hotter and more damaging than they used to be. And I think I have a picture here. Well, this shows the coevolution of some plants, of some organisms, and fire. These are aspens regerminating after fire in the Met-How. I forget where I took this picture, but it is here in the Met-How. This is what happens. Aspen just naturally regenerates from the roots after a fire. So what you end up with instead of old trees are young, more dynamic trees. So fire reinvigorates the aspen stand. And that is true for our conifers to a different degree. So that's an article that was in the Naturalist, Dying to Burn. Lodgepole pines are arguably dying to burn. They have a lifespan of about 100 years. They live from 70 to 100 years. They die and they become highly flammable when they die and dry out. I mean, they're flammable in any case, but they're more flammable when they die. It creates a stand replacing fire. Lodgepole pine cones open at something over 100 degrees. So the fire causes the lodgepole pine cones to open and drop seeds on the ground, on the fertile ground after the fire has gone out. So it's fire evolved. These trees are evolved to live with fire. That is ponderosa pine. That's Leah, for those of you who know Leah. That picture was taken a while ago. But ponderosa pines are co-evolved with fire. They have bark that can be up to 10 inches thick. Often fire can sweep through an understory fire and not affect the tree. If it does affect the tree often, first branches are often 30 or 40 feet up in the air. Tree doesn't get into the canopy. The fire doesn't get into the canopy. The tree survives, and it creates these interesting fire scars, which are widespread. Now, in the back of that picture are half a dozen young Douglas fir, and I think the next pictures deal with this increase in organic matter because of fire suppression. Did I go forward? Yes. This is a map of the increase in fire periodicity in the last 50 years because of the buildup of organic matter. So an interesting point here is our culture didn't really know about this, and I think we get to a slide or two about Native Americans lit fires regularly. They knew that fire was a natural part of the environment. They knew that if organic matter built up too high, they would have catastrophic fires. So they lit fires every year when conditions were right for being able to control the intensity of the burn. This just shows that fires are a natural part of the ecosystem. I love this insight called shifting baselines, created by this marine biologist, Dr. Daniel Pauly. So basically saying humans change the environment over time, but we're not aware of the changes. How many of us are aware when we walk through the forest how all the large ponderosa pines are undergrown by Douglas firs? It just looks natural to us, but it's arguably not natural. So here's Here's a natural state of a healthy ponderosa pine forest, which will experience underburns naturally, not set by humans, naturally every 10 or 15 years. So there's no undergrowth. There's no Douglas fir coming in. There's almost no young ponderosa pines. There's no bitterbrush. There's no sagebrush. The grass is short. Probably had a burn in the last 10 years. It's a natural part of ponderosa pine fire regime. Here's a ponderosa pine. This is up at Sun Mountain. I remember taking this picture. It's in the parking lot. I'm sure it still looks like this, where fires have been suppressed for 100 years. And what happened? Trees that are trees that can grow in the shade, the Douglas fir grows in far shadier situations than ponderosa pine, have somehow come in large numbers and grown in under the ponderosa pines. So now this tree is surrounded by young Douglas fir, which creates a ladder fuel. If there is a fire, the fire will burn up through the Douglas fir and into the crown of the ponderosa pine and kill it. So we had no intention of creating these changes, but we have created these changes. It's what's that term? Shifting baselines. We don't see it happening. Well, we are getting onto it, as you know. We're becoming aware of these changes. Here's another picture. There's also probably at the parking lot in Sun Mountain. There's a lot of these big ponderosa pines completely surrounded by young Douglas firs, which will burn with a fury and transfer the flames into the crown of these ponderosa pines, which very thoughtfully have dropped all their lower branches to keep fire from getting into the crown. See, there's no branches on either one of those ponderosa pines. They drop off naturally over time, but it won't work in this time because of the young Douglas firs coming in. So a good intelligent response are prescribed burns. And we now burn a very large amount of acreage naturally throughout the West to try and recreate these natural conditions that existed before human intervention, before humans started putting out fires. It's understandable that we put fires out, but it's not working out. And so to plan for it with a prescribed burn and fire breaks and fire trucks in the area has worked pretty well for us. A few prescribed burns have gotten out of control, but typically these fire managers are very good at what they do. I think you've seen this before if you saw last week's program. I happen to really like this graphic of oxygen content in the atmosphere over time. I think I have a little red circle here. So I pulled up a little red circle on the bottom left. It just to illustrate the timeline. That 4.5 is 4.5 billion years ago. So those are billions of years before the present. Oxygen in the atmosphere. How much oxygen was there in the atmosphere 4 billion years ago, 3 billion years ago? None. There was no oxygen. Why? Because oxygen is very reactive, as we've said. It won't stay in the atmosphere unless it's constantly pumped there by living organisms. What's doing that? The photosynthetic organisms on the planet give off oxygen. It's always said as a waste product, but that's really not correct. It's not a waste product. It's at least a byproduct because it's part of a biogeochemical cycle that is utilized by living organisms and transformed into other chemical properties. So it's not a waste product, but it is something to pay attention to. So this is a graph of oxygen content in the atmosphere over time from 4.5 billion years ago. It started out at 0. There was no organic matter. It went up to 10%. It went up to 20%. And then there was a time, half a billion years ago, 500 million years ago, during the Cambrian explosion, when the oxygen content in the atmosphere spiked to almost 30%. Apparently, above 25%, organic matter will burn even if it's wet. And so probably, I think it's not known what caused the spike entirely, not entirely known. And it's not entirely known what caused it to return down to 21%, which is where we're at today, 21% oxygen in the atmosphere. But fire is implicated. things burn so readily at above 21% oxygen, 25% and above, fire consumes oxygen and lowers the flammability of the atmosphere and of organic matter. So there's a natural built-in balance to the amount of oxygen in the atmosphere due to flammability and fire. There's the 21%. So I circled above there at the top. It says aerobic eukaryotes. We talked, I don't know if you remember, some of you know, and some of you may not remember. Life has basically had these two cellular life forms, prokaryotes and eukaryotes. Our cells are our body cells are made of this eukaryotic type that they're larger, much larger than prokaryotes. They have a nucleus. Prokaryotes don't have a nucleus, but they still complicated. And aerobic eukaryotes means learn to use oxygen for biochemical reactions in the body, for breaking down organic matter and harvesting the energy. But they weren't always here. Maybe that's one of the things there. You can't have aerobic eukaryotes until you have a high oxygen content in the atmosphere. So while fire has been not always a friend, it has made us human. And I would agree with the concept of Richard Wrangham in this very interesting book, which is the cover is shown there, Catching Fire, How Cooking Made Us Human. Humans began utilizing fire. Humans, not, let's see, I forget the actual, I think there were no Homo sapiens. It would have been more like Homo habilis and Homo erectus. Let's see what we have here. 1,000,000 years ago, humans began taming fire and using it for beneficial purposes for our species about 1,000,000 years ago. And that would not have been Homo sapiens, which didn't exist at that time. It was earlier existing Homo species, habilis and Homo erectus. But it has everything to do with human evolution. For one thing, taming fire and using fire at night made the night much safer from the large carnivores roaming the African landscape, lions and tigers and bears. Not so many bears, but lions and tigers, because they're afraid of fire and they wouldn't come in at night. But more than that, when we started cooking food, I forget the timeline on that, but when we started cooking food, it made the nutrients and the energy bound up in that organic matter, the food itself, far more available to our bodies so that we had more energy available to us. We didn't have to eat as much and we got more energy out of the food we did eat. And there is a connection between the rapid expansion of the size of the human brain and the energy available from cooking food. So that's part of what Wrangham deals with in this book is the cognitive abilities that our large brain grants us is related to harnessing fire to cook food. So photosynthesis, it's a great process. It's a nice word. I like it a lot. So synthesis means to create, right, to synthesize something, combine something into something else. And it's done by the energy of light, photosynthesis. So photosynthesis harnesses the energy coming from the sun to actually break water molecules apart, shown there, H2O, break water molecules apart, transfer the hydrogen to the CO2, so you get CHO, which is sugar. Photosynthesis is a process of transferring carbon dioxide and water into sugar. You end up with an additional element, what they would call a waste product. Oxygen has been freed of the hydrogen atom and turned into O2 and released into the atmosphere. And the only reason, as I've said, the atmosphere is 21% oxygen is because of photosynthesis. It's a highly reactive molecule, O2, and it wouldn't last in the atmosphere for a long time without constantly being pumped into the atmosphere. So this is the reverse of photosynthesis. You're starting out with that hydrocarbon, which is sugar, CHO, on the left, which was created by photosynthesis. You're introducing oxygen into the chemistry of the arrangement, and they react because oxygen is so reactive, and you end up with these these products of the reaction: carbon dioxide and hydrogen, water, H2O, which is what you started with, and the energy that was captured by the process of photosynthesis, captured in the hydrocarbon bonds through the process of photosynthesis, is released, and that's what makes our life possible.
Makes life possible. Is what makes life possible. Photosynthesis up above and cellular respiration down below. Opposite chemical reactions. It's a big circle.
Talk about
photosynthesis makes hydrocarbons.
Oh yeah.
Cellular respiration turns
Is that you,
hydrocarbons into
Philip?
water, CO2,
Yeah.
and energy. So plants know.
Let's talk more about it at the end.
You know, what's kind of amazing is that animals actually came first. It depends on how you define animal, but I always assumed
the whole process is highly impressive. I have to say.
I always assumed that plants came first because
Yeah.
animals eat plants, right? So plants had to already be there for animals to eat. And I never even thought about whether animals somehow came from plants or just arose separately or what. I mean, it's amazing enough that life arose at all, but that could they have just both sort of arose independently, or
how'd that work?
how did that happen? Well, it's not easy to say because soft parts don't fossilize.
So here we have
really early life.
One is
all we know is there were large mats of.
I'm assuming you can hear me. One is this moss, brim. This grows. I took this picture. It grows right here in the Manhaw Valley. It's just an example of how diminutive photosynthetic organisms can be. It's a tiny little moss. It grows a few millimeters high on the rocks. This is probably a Baki Hill, actually. And those are reproductive structures standing up there. But the whole reason for its existence is this ability to harvest the energy of the sun by the process of photosynthesis. But the story, so early photosynthesizers were small, like this brim moss. They're not so small anymore. Here is a giant sequoia, which weighs 4 million pounds. Unbelievable product of photosynthesis, made largely out of carbon dioxide in the atmosphere, which is interesting to me because carbon dioxide is not, even though we're worried about carbon dioxide levels in the atmosphere, and I forget exactly, they're like 425, 450 parts per million. The tree is made out of carbon dioxide, largely. I wrote it down, I don't remember, it may be 90% carbon dioxide out of something that exists in parts per million in the atmosphere. It's an impressive arrangement. This is a formula for wood, lignin, which is created through this process of photosynthesis, probably first creating sugars and then transforming the sugars into something more durable, lignin. But what's interesting to me in this formula is all that's in there is carbon and oxygen and hydrogen arranged differently than they might be in a sugar. But it's the same components is what wood is made out of. And you can see that it's got a high level of complexity to it. And it's very hard for organisms to break down. There are very few organisms that can eat wood. You might think of termites can eat wood, but termites only can do it because they have bacteria in their guts that actually break down the lignin. I don't know. I don't think there's any large animal that can actually break down lignin. It's a complex molecule. And that's a molecular model of lignin. So here we have that photosynthetic process where carbon dioxide and water, the hydrogen's transferred to the CO2, oxygen's released in the atmosphere. You end up with sugar, which can be then complexified into starch and even lignin. This is the original process. But what happens if some of that byproduct of photosynthesis, the sugar, is buried? You've released the oxygen into the atmosphere, and over time it would react with that byproduct of photosynthesis. I'm calling it sugar, but it can be other things. It's the oxygen that would react with it and break it back down into carbon dioxide and water. But in what actually happens is some of this organic matter over the span of the 400 million years that plants have existed on the planet, that large plants have existed, some of it is always sequestered as organic matter in the earth, and which can start out as simple organic matter in the soil, but over great lengths of time may be compressed into turn into coal. Coal is a product of organic matter. Natural gas is a fossilized form of organic matter. So in a sense, what we've done, what life has done is it's sequestered some of the carbon as organic matter and released the oxygen in the atmosphere. And that's why oxygen has increased in the atmosphere over the last 3-4 billion years. So I think I circled here. This is energy consumption by Homo sapiens over time. So the bottom line is a bottom axis is a time axis starting at 1800, the year 1800, 1850, 1900, and up to about the present 2019, 2020. It shows the increase of human energy consumption over time. And the numbers are obviously gigantic. I circled, so Homo sapiens have been evolving. I think our species is approximately 100,000 years old. For all of that 100,000 years old, 100,000 years, we lived on traditional biomass. We used wood for fires to cook our food and heat ourselves. It's only in the last, using this graph, 120 years that we've tapped into the hydrocarbons that were stored as fossil sunlight. It's often called that, fossil fuels. They're called fossil fuels because they're fossilized sunlight. They fossilize those hydrocarbon bonds that have energy bound up in the bonds in the ground in these various formats: coal, oil, natural gas. And it was quite a discovery 150 years ago that we could access the energy in these fossil fuels and release them to our own benefit, at least in the moment, But obviously over time, it's become a bit of a problem for humanity because two reasons. One is that fossil fuels are finite, and we cannot continue this trajectory actually for much longer. I forget the estimates, but I would say 40 years. 40 years is a long time to continue this upward trajectory. It's unlikely to occur because fossil fuels are finite. Also, they're hydrocarbons, and when you burn them, it releases carbon dioxide in the atmosphere, which has created the buildup of carbon dioxide. So it's a double-barreled conundrum for us to address. So I decided to put in this a picture. I went out last night and took this picture of my solar panels. I'm not offering this as an answer to the problems of human energy consumption, but there are ways, simple ways to respond that at least address the problem and reduce energy consumption. So I get most of the electricity for my house from these two solar panels, which have been here. Those solar panels have been there for 20 years, which is a notable point. They last a long time. I also have a generator that runs on gasoline when I need it. If my batteries get low, it's another semi-cloudy day today. I'm sure I'm just coasting now on yesterday's sunshine, and by evening I may have to turn the generator on. In any case, it's an effort to address this problem of massive energy consumption that we've grown so used to in our culture. So, what's it all about? This is one of my favorite cartoons. Well, it's about eat, survive, reproduce. That is what most of life on the planet is concerned with. And I don't want to make the argument that Homo sapiens are the only one to ponder this question, but we are unusual in our ability to contemplate life on Earth, our place on life on Earth, natural ecobiological cycles and with the ability to try and learn to live ecologic on the planet. I would say it's highly possible for Homo sapiens to do that. We're moving in that direction, but not fast enough. So that's my summary. And let's see here. What do I have? Nothing. Okay. That's the program. Hope you enjoyed it.
Thank you, Dana.
So we could possibly take questions and comments like Phil. Phil, I couldn't quite get what you were saying. I don't know if you, what do I do? Stop share? I'm interested in chat. Let's see.
Yeah. Phil, we would welcome you to unmute yourself. And I'm sorry I interrupted when you were sharing some thoughts.
Not at all. Well, I see in the chat, and we noted this last week, but the book's available for free. It is a worthwhile book to read. You can download it for free, and the link is in the chat. Or if you can't get at it, you can email me and I'll send it to you. Oh, thanks, Susan. Well, there's not too much chat. Oh, I'm glad that cross-country ski thought that was worthwhile. It's tough to address that stuff, it's somehow we can understand it, I think, but it's just complex and it's things we don't typically think about. That all of the dynamics of the planet are driven by this nuclear reactor 183 million miles away, speaking of the sun. It's a fascinating arrangement, life on Earth, and it's worthy of contemplation. So I don't see any other. If anybody wants to pipe up, raise your hand.
Yeah, if anyone wants to unmute, you're welcome to and ask a question or share a comment.
I don't know what happened there.
You can raise your hand or just go for it.
I'm reacting to the fire graph from Forbes magazine
Oh,
that suggests that lack of frequent burning is the only problem, as if climate has no factor in increasing fires. But even though it is true that lack of regular burning does make the fires possibly more severe, the fact that the climate is warmer and drier clearly it is a big factor. So that graph kind of bugged me because it was there was some little subtitle on it that made it clear it was in aim of saying climate is not the problem.
Susie, for reasons unbeknownst to me, I could not hear you. The volume was so low, but maybe Donna, could you hear?
I could.
Can you summarize or no?
Susie was sharing the graphic or commenting on the graphic you shared about fire. And that
the bar chart from Forbes.
Yeah, the bar chart. Yeah. And highlighting that it really didn't highlight the environmental change or the climate change as part of the reason.
Yeah, that they were arguing in some way. There was some little subtitle on it that made me think they're trying to argue that lack of prescribed burns or regular burning is the problem, and that climate doesn't have anything to do with it. But I don't buy that. It's certainly, lack of regular burning is a factor, no question. I'm not questioning that. But to say that drying everything out and heating everything up doesn't make a difference. It really does.
I still can't hear. What'd she say?
Oh, too bad.
Oh, yeah, darn, I'm sorry. I'm sorry you're not able to hear. Can you hear me, Dana?
Yeah, I hear you plainly, and I don't hear Susan for some reason, Susie.
Okay.
I don't know why.
It was harder for me to hear Susan, but she was just commenting that the graph really highlights that prescribed burning is important, but it didn't really talk about or infer that global warming has had an effect as well, which she's just sharing that,
Okay, so thanks, Susie. I get that, and I appreciate that comment. Yeah. And all these things, I mean, as Ferris would be the first to say, the author, Ferris Jobber, all these things are interconnected. Global warming is to the degree that it's occurring is largely driven by carbon dioxide in the atmosphere, which is largely driven by our consumption of hydrocarbons, which were a great invention for humanity, but now become a curse. There's just this interconnectivity, and it's all asks us to learn the ecological rules of life on Earth. I mean, that's the only solution is learning to live ecologically on the planet. And it is highly possible to do. I mean, like, well, that one graph that showed consumption, I can't find it and I forget exactly what it was, but through the history of humanity, our consumption of organic fossil or of hydrocarbons has been very low. It just has shot up in the last 100 years. Sure, I can find that. This one.
yeah, that graph really puts it into perspective.
Now, we should point out that the human population has risen in tandem with that.
Mm.
That the almost 9 billion people on the planet are now supported largely by fossil fuels. So we painted ourselves into a corner. That's the way it goes. Maybe we can find a way out. I mean, part of the problem is the level of consumption that the Western world engages in. That's one of the reasons this shoots up. I mean, a lot of this is petroleum. A lot of the third world doesn't use petroleum. It doesn't have any access to it. Anyhow, these issues can be addressed, and the capacity of humanity for ecological thought and intelligence can respond to these problems and is trying to. So there is hope, and it's a good challenge, but it is a challenge. It's my summary statement.
Well, I'm very glad to hear that you are hopeful. Because yeah, we have a lot to figure out.
We do.
Anyone else have a comment or question to share with Dana?
Those are pinnipeds in the background, by the way. Which are seals.
In the background on your wall?
Yeah, can you see that chart on the background?
Barely, but a little bit.
Oh. Yeah. Well, you can't focus on it, but you can see it's there.
Yeah. Yeah.
Yeah. Life is so rich and intriguing. So that includes the pinnipeds, and down below, over there, those are penguins. Part of the biodiversity of life on Earth. Okay, we may be wrapping up.
Yeah, well, thank you so much, Dana, for getting us all to think deeply about this tough question, life on Earth.
Yeah.
And how we are going to work towards, hopefully being able to sustain in some way.
Yeah, sustain's a good word. We talk about a sustainable society. That's what we're after. Susie, do you have your hand up?
Say that one more time.
Looks like Susie has her hand up. Maybe she's waving goodbye.
Oh, okay.
No, I was clapping.
That might have been.
Oh, she was clapping.
Oh, you were clapping.
Say thank you.
That's great.
Thank you, Jane.
Thank you all for participating. See you out and about.
And I will just share. I assume many of you know that Dana publishes The Naturalist 4 times a year, every quarter, and the new one comes out in March. Is that correct, Dana?
Yes.
Yeah.
On the equinox.
So if you are not a current subscriber and are interested, you could email Dana. Is that right? To get on your mailing list?
Yeah, you could email me. I'll send you a free copy. Thanks for the pitch.
Yeah. Yeah. Well, it's a very, very interesting publication. So thank you for doing that.
Yeah. Well, thanks to everybody. I'm going to go have lunch.
Oh yeah. Yeah, you couldn't eat while you were talking,
No,
could
I
you?
didn't want
Like
to be.
all of us could. Yeah.
Nice to
Okay.
be hungry though.
Yeah. Thank you so much, Dana. We'll take
Yeah.
care and enjoy the rest of the afternoon. And I hope everyone gets to read the book.